Hello everyone. So for today, our topic would be non-exact differential equations. So what is a non-exact differential equation? So let's define it. So we consider the given, we consider the differential equation mxy dx plus nxy dy is equal to 0. If the given dE is non-exact, then the partial derivative of m with respect to y is not equal to the partial of n with respect to x. We have discussed earlier on non-exact differential equations that the partial of m with respect to y should be equal to the partial of n with respect to x. So a non-exact differential equation is basically if we test for exactness and the partial of m with respect to y is not equal to the partial of n with respect to x. In theory, there exists a function phi such that if the function phi is multiplied to both sides of the dE, it will now yield a new equation that is now exact. Hence, if you multiply the partial, if we multiply the phi to the given differential equation, that is mxy dx plus nxy dy, then this new differential equation is exact. With phi being called the integrating factor. So basically, in summary, we have a differential equation, mxy dx plus nxy dy is equal to 0. We test for exactness, and we found out that the partial of m with respect to y is not equal to the partial of n with respect to x. However, we can solve for a function phi such that if we multiply that phi to the differential equation, then we now have a differential equation that is exact. So our goal first is to check for exactness. If it's not exact, then we find the phi, or it is also called the integrating factor. Okay, so there are many cases or methods of solution for finding phi. So these are the methods of solution for finding phi. So the first method is called case 1, where phi is equal to phi of x. If, so this is the formula for the first case, 1 over n times the partial of m with respect to y minus partial of n with respect to x is equal to f of x. So in the first case, the partial of m with respect to y and the partial of n with respect to x are basically values or expressions that we already know by checking for exactness. So we'll try to get that value, then we'll multiply 1 over n, and the choice for case 1 or case 2 will highly depend on where the or where of the two expressions, m or n, will, if you multiply 1 over that expression, in our case, on the first case, that's n, will that n cancel out anything on the partial of m with respect to y minus partial of n with respect to x? So that's how we pick cases. Next is so this is the first case, and case 2 would be phi. So we're finding for phi such that phi is phi of y. So this is the given formula. So for case 1 and case 2, we basically select So the only difference between the two is that this part right here and this part right here. So in order to choose between the two cases of which of the two cases are you gonna use, you will have to inspect if the m under the differential equation can cancel out anything when multiplied to the given partial of m with respect to y minus partial of n with respect to x. Since this part right here is also the same as this part right here. So you will only need to inspect whether n or m would cancel out anything on the given partial of m with respect to y minus partial of n with respect to x. Next is case 3. So case 3 basically says that phi is equal to x raised to m y raised to n, where m and n are in the positive or are in the set of integers such that partial of m with respect to y minus partial of n with respect to x is equal to m sub n, or small m big N over x minus small n big M over y. And we solve this by basically having to equate the coefficients of the left side to the right side. So this is solved by equating coefficients. So in order to show how it's done, how to solve non-exact differential equations, let's try to have an example. For our first example, we have x squared plus y squared plus x dx plus xy dy is equal to 0. So the first step is to always check for exactness. So let's check for exactness. To check for exactness, we have to find the partial of m with respect to y and also the partial of n with respect to x. So we have to solve for the partial of m with respect to y. Let's look at m. So this is m and this is n. Okay, so now the partial of m with respect to y is, so the partial of x squared with respect to y is basically just 0, since the derivative of x squared with respect to y is just 0, since there are no y variables whatsoever besides x squared or multiplied to x squared. There are no y variables. So x squared is just considered as a constant. Therefore, the derivative of constant is 0. The next one, let's have the derivative of y squared with respect to y. So that is 2y using power rule. And the derivative of x with respect to y is 0. Next is the derivative of xy with respect to x, so that is n with respect to x. So the derivative of this is basically take out the constant, which is y in this case, then get the derivative of x. So that is 1. Therefore, partial of m with respect to y is 2y, and the partial of n with respect to x is y. Therefore, the dE is not exact. Now, we have seen from the previous cases that there is a common expression from all the cases. That is the partial of m with respect to y minus the partial of n with respect to x. So, knowing that this is the common expression from all the three cases, then we need to solve for this. And since we already have the partial of n with respect to y and the partial of n with respect to x, we can just solve for this directly. So we substitute 2y to partial of n with respect to y, and we substitute y to the partial of n with respect to x right here. So we have 2y minus y, which is y. Now the next thing that we're going to do is to pick a case between all the given cases. So in order to know what case to use, we should basically inspect we should basically check m and n of where does these two do you multiply the partial of m with respect to y minus partial of n with respect to x, of which of those two, m and n, will y be cancelled out if you multiply one of those two. So 1 over which one of those two, m or n, should I put here, such that if I substitute m or n right here, I can cancel out the y. So that would be n. Since n is a monomial and also has a y that is multiplied to the x. So that's why we can cancel out y right here. And this is equal to f of x. And this is case 1, where whatever is multiplied here is 1 over n. Okay, let's try to rewrite this. So this is case 1, 1 over n times this part. So we have y right there is equal to f of x. Then we substituted xy to n. So we have 1 over xy times y is equal to f of x. So we cancel this out, and we are left with f of x is equal to x. Now the next step would be to solve for the integrating factor. So the integrating factor is basically, for case 1, that is phi of x. So v of x is e raised to the integral of f of x dx. So this is now equal to e raised to integral of x dx. And the integral of x dx, or sorry, this is 1 over x. The integral of e raised to integral of 1 over x dx is e raised to ln x. So e raised to ln x, basically, if we can remember, we have a property for exponential and logarithms where you can basically have, if we have something like e raised to ln, any expression r, then we can basically say that we can bring down the r and e raised to ln is now removed. So we just bring down the r. In that case, or for our case, we now have x, since we bring down the x using this property. So now, multiply the integrating factor to our differential equation. So we multiply the integrating factor, phi of x, to the dE. So we would have x times this part plus x times this part. So we simplify, we would have x cubed plus xy squared plus x squared dx. Plus x squared y dy is equal to 0. So this time, let's check for exactness. If what we had is really, or if it really becomes exact after we have multiplied the integrating factor. So let's check that. So let's check for exactness. Partial of m with respect to y is equal to, and let's also get the partial of n with respect to x. So the partial of m with respect to y, we get this. So that is x cubed is a constant, so that becomes 0. And on this case, we take out the x, then we try to get the derivative of y squared with respect to y, so that is 2y, and x squared also becomes 0. So we are left with 2xy. Now for the case of the partial of n with respect to x, we will have take out the y, then get the derivative of x squared with respect to x. So that is 2x. So we are left with 2xy. They are equal. So now the dE is now exact. So now that the dE are now exact, then we can have the different methods of solution. So now we have three different methods of solution for finding the general solution for our new differential equation. Our new differential equation, which is multiplied by phi. So let's choose which of those methods can we use so that it is easier for us to integrate and differentiate either expression m or expression n. So we select between the two, and it is actually easier to integrate and differentiate expression n. So the method that uses expression n is method 2. Okay. Now method 2, let's just get the n, which is x squared y. Then we need to solve for f of xy. The f of xy actually gives us the general solution. So f of xy is equal to the integral of n, which is x squared y, dy, plus h of x. Okay, now let's get the integral of x squared y with respect to dy. So let's take out the x squared, since the x squared is a constant when we're integrating with respect to y. Then let's get the integral of y, and that is y squared over 2. So now we simplify. This is x squared y squared over 2 plus h of x. This is equal to f of xy. Now, this is not yet our answer for the general solution, since we don't know the value of h of x yet. So we need to solve for the value of h of x. And in order to do that, we first need to get the partial derivative of f with respect to whichever is the variable inside the function right here. So the variable inside h of x, or the variable inside h, is basically x. So we get the partial derivative of f with respect to x. And this gives us, so in this case, get the partial derivative of x squared y squared over 2. We take out the y squared over 2, since we consider that to be the constant. And x squared, let's get the derivative of x squared, so that is 2x. plus h prime of x. We simplify even further. We cancel out 2 right here, and we're left with xy squared plus h prime of x. Now, the partial derivative of f with respect to x is actually the phi mxy. Let's also change this up. Since this nxy that we've used is now the new nxy from our new differential equation. So let's use phi nxy and phi mxy. We have shown this to be the case during the discussion for the exact differential equations. Okay, so now we equate the two. Xy squared plus h prime of x is equal to the phi of mxy. That is basically x cubed. So let's copy phi mxy. Phi mxy is basically x cubed plus xy squared plus x squared. So now, by inspection, let's try to see where, or let's try to see what the value of h prime of x for these two to be equal. So for these two to be equal, the left side and the right side, h prime of x would have to be the missing number, the missing expressions or terms from the right side, since the right side is the more complete expression. So h prime of x is equal to x cubed plus x squared, since x cubed and x squared are not found in the left side. Okay, so h prime of x is equal to x cubed plus x squared. Therefore, the next step is to find h of x. So we now have h prime of x, and in order to find h of x, we would need to integrate h prime of x. Which is the integral of x cubed plus x squared dx. This is now equal to x raised to 4 over 4 plus x cubed over 3 plus c, using power rule. Now that we have h of x, we could now substitute that to our fxy so that we can have our general solution. So our general solution is basically fxy is equal to, copy this one, so we have x squared y squared over 2 plus h of x. So h of x becomes this part, x raised to 4 over 4 plus x cubed over 3 plus c. Then we now have our general solution. Okay, so that's all for example number 1. So for the next example, let's have number 2, 2x dx is equal to 1 minus x squared plus 1 cotangent y times dy. So the first thing that we're gonna do is basically we can rewrite this as 2x dx equal to negative x squared plus 1 plus 1. So I basically just swapped their places, this one plus this one. Okay, so that when I add this part, both sides, so we can have the form mxy dx plus nxy dy. So I'll just transfer this right here. We'll have 2x dx plus x squared plus 1 cotangent y minus 1 dy is equal to 0. So I transferred this right here. I transposed it, meaning this becomes positive. So that becomes positive. And this part right here becomes negative. Okay. So the next step would be to check for exactness. So for checking of exactness, let's have the partial of m with respect to y. So this is m. We have 0 since the derivative of 2x with respect to y is just 0 since 2x is a constant in that case. Next up, we have the partial derivative of n. So this is n with respect to x. So first off, we factor out the cotangent y. Then we get the derivative of x squared plus 1 with respect to x. So we'll have 2x minus, so minus 1 becomes just 0 since the derivative of constant is 0. So these two are not equal. Therefore, the dE is not exact. So in order to make it exact, we should find first the partial of m with respect to y minus partial of n with respect to x. So this is 0 minus cotangent y times 2x. So we have negative 2x cotangent y. Now the next step would be to solve for the integrating factor. So for solving for the integrating factor, we'll pick a case, either case 1, case 2, or case 3. In this case, we'll pick case 2. Since for case 2, the easier, or when we actually pick between these two, m and n, case 2 is only a monomial, so it is easier for us to divide a monomial, which is 2x. So our case 2 looks like this. Negative 1 over m times the partial of m with respect to y minus partial of n with respect to x, which is Negative 2x cotangent y is equal to g of y. Now, in this case, m is a monomial, so we will have negative 1 over 2x times negative 2x cotangent y is equal to g of y. Now, we have a negative 2x right here, negative sign and 2x, so we can cancel them out. So we have negative and the 2x, so this negative and negative becomes positive, and we'll have to cancel out the 2x that is common between the two. Then we are left with g of y is equal to cotangent y. Now for case 2, phi is phi of y. So this is equal to e raised to the integral of g of y dy, which gives us e raised to the integral of cotangent y dy. Now cotangent y can be expressed as cosine y over sine y dy, and we can use u substitution such that we let sine be u, since we can find the numerator cosine y as its derivative. So the derivative of sine y dy, or the derivative of sine y, is basically cosine y dy, and we can find cosine y dy right here. So this becomes e raised to du over u. Now the integral of du over u is basically ln u, but u is sine y, so we have e raised to ln sine y. And when we simplify this using the property of logarithm, we would have just sine y. So now we have the integrating factor, which is sine y. So phi of y is equal to sine y. Now we multiply the integrating factor to the original dE. So we multiply the integrating factor to the original dE, which is this one. So we would have 2x times sine y, we would have 2x sine y dy, plus sine y times this part, so we would have x squared plus 1 cotangent y sine y minus sine y dy is equal to 0. Now 2x sine y dy plus this part, we can just simplify this. Cotangent y times sine y. Cotangent y actually becomes cosine y over sine y. So we can cancel this out. Then we just simplify even further. Now right here, we now have our new differential equation. So from our new differential equation, let's now have the methods of solution. Or let's just first check for exactness actually. So let's check for exactness. So for checking of exactness, let's find the partial of m with respect to y and the partial of n with respect to x. Partial of m with respect to y is basically, so 2x, if we factor out the 2x, okay, then we get the derivative of sine y, so that is cosine y. And the same goes for this part. We get the partial derivative of n with respect to x. So first off, we factor out the cosine y, since we consider that to be a constant. Then we get the derivative of x squared plus 1, which is 2x. So this becomes 2x cosine y. Now when we compare these two, they are equal. Therefore, the DE is now exact. Now that the DE is exact, then we can have the different methods of solution. So let's have the different methods of solution. So in our case, the easier to integrate and differentiate would be this one. So for this one, the m, the method that is more suitable for that, or the method that uses that, is method 1. So our m is equal to 2x sine y. Now let's get the fxy, which is equal to the integral of mxy, so that is 2x sine y dx plus g of y. Now let's simplify. We factor out the sine y, since it is a constant when we are integrating with respect to x. Then we get the derivative of 2x, which is 2 times x squared over 2 plus g of y. So we'll have, cancel this out, we'll have x squared sine y plus g of y. So our fxy is this one. Now the next step would be to get the partial derivative of this function f with respect to whatever variable is in the function g. So we'll have partial derivative of f with respect to y. So this is phi as a correction, but as a correction, this is phi of m, since we have multiplied phi to m and n, or to the whole differential equation. So partial of m of f with respect to y is basically we get the partial derivative of this with respect to y. So we take out the x squared, since it is a constant when we're integrating with respect to y. Then we get the derivative of sine y, that is cosine y, plus g prime of y is equal to, now partial derivative of f with respect to y is actually the partial, or this is basically phi of n of our new differential equation. Now we substitute that. Phi of n. So phi of n, let's try to look back what the value of phi of n is, or what the expression of phi of n is. This is the phi of n. So we have x squared plus 1 cosine y minus sine y. Okay, so this becomes x squared cosine y plus g prime of y is equal to x squared cosine y plus cosine y minus sine y. We cancel out x squared cosine y, and we're left with g prime of y is equal to cosine y minus sine y. Now the next step would be to get g of y. So g of y is actually the integral of g prime of y, which is cosine y minus sine y dy. We get the integral. This is the integral of cosine y is basically sine y, and the integral of negative sine y is positive cosine y. Since the derivative of cosine y is negative sine, then the integral of negative sine is the positive cosine, plus c. So now our general solution is fxy is equal to, copy this, x squared sine y plus our g of y, which is now this part. So we have sine y plus cosine y plus c. And that's all for example number 2 using case 2 of finding the integration, or what do you call that, the integrating factor. So for our next example, let's have 2x squared y, 2x squared over y squared plus 1, or sorry, plus 1 dx plus x over y dy is equal to 0. Now first that we need to do is we need to check for exactness. So when checking for exactness, let's get the partial derivative of m with respect to y, and also the partial derivative of n with respect to x. Now when getting the partial derivative of m with respect to y, let's start with this first. So let's factor out the 2x squared, since that is the constant part. Then we get the derivative of y squared, which is actually, we can rewrite y squared to be, so 1 over y squared. We can rewrite this to be y raised to negative 2. So this becomes 2x squared times the derivative of y raised to negative 2 is bring down the negative 2, then subtract 1 to the exponent negative 2. So we will have negative 2 minus 1 plus the derivative of 1 with respect to y, which is 0. So this becomes negative 4 x squared y raised to negative 3, or this becomes negative 4 x squared over y cubed. Next, let's find the partial of n with respect to x. So this is n. This becomes, take out the 1 over y, then we get the derivative of x. So that's just 1. So this is the partial derivative of n with respect to x. Now they are not equal, so the dE is not exact. So now that we know that the dE is not exact, let's use the 3 different cases, or let's pick one of the 3 different cases, case 1, case 2, and case 3, to solve for the integrating factor. But first, we need to find the partial of m with respect to y minus the partial of n with respect to x. So this is equal to negative 4 x squared over y cubed minus 1 over y. So in this case, that if we have a partial derivative of, or if this part is equal to a fraction such as this, and our given is full of fractions, then the best case might be case 3. So case 3 is mainly used for those that have intensive or many fractions. So let's use case 3. Case 3 indicates that phi is equal to x raised to m, y raised to m, such that m and n are in the set of integers where the partial of m with respect to y minus partial of n with respect to x is equal to the small m big N over x minus the small n big M over y. Okay, so now we know the value of this part, so let's just substitute that. So we have, okay, so now what we're gonna do is basically substitute what we had. So partial of m with respect to y, this part right here is actually this part, so let's just substitute that. We have negative 4x squared over y cubed minus 1 over y is equal to small m times big N. We know big N to be x over y over x minus small n times big M. We know that to be this part right here. So we'll have something like this. Okay. Now moving on to the next part, we'll just copy this. Then basically simplify. I distributed the n. So now we simplify. We have a denominator, or sorry, this is x. We have a numerator that is x, and we have a denominator that is x also. So we can cancel them out. So we are left with m over y minus this part right here. You can actually rewrite this part. You can actually rewrite this part as two x squared n over y squared plus n times 1 over y. Since when we divide, we just get the reciprocal of it and we multiply it instead. So we simplify, we'll have, or we distribute, we'll have 2x squared n over y cubed. And since we also have a subtraction symbol right here, then we also distribute that to n. So we'll have minus n over y. So we simplify, we'll have, so our goal here is to basically have the same form on our right side with the left side of our equation. So in order to have this form, let's move this part right here with the y cube of the denominator on this side right here. So we'll have something like this, plus, so m over y and n over y are of the same denominators, so we can combine them as one fraction. So we'll have here m minus n. So now, let's observe our given left side of the equation. We have negative x squared y cubed on the same, on the right side and also on the left side. So they are of the same form. So we are now okay, or we are now complete on this side of the equation, on this part of the equation. This is now good. Now let's observe this one. They have the same denominators, but they don't have this minus sign right here. So in order for me to be able to make that minus sign appear, then I should multiply a minus sign and another minus sign, so that this is equal to just the positive. But I did this so that I can make that minus sign, or that minus over y appear, which is something that this left side of our equation has. So we'll have minus minus m minus n. So we simplify even further. Now we have negative 2x squared n over y cubed minus, in this part we have, so the negative sign times m and the negative sign times negative n. So we'll have negative m plus n, or basically just n minus m over y. Okay, so this is the same as negative m plus n over y. Okay, when we distributed this negative sign. Okay, so the next step would be to drag down or to compare the left side of the equation to the right side of the equation. So this left side has negative x squared y cubed, and this expression also has negative x squared y cubed. In the same way, this expression has negative the denominator of y, and this expression also has negative the denominator of y. So we can equate coefficients. So we can now equate coefficients. So for this side, we can equate these two. So 4. So the only thing that is not common, you will equate those. So in this case, we have 4 and 2. So you have 4 and 2n actually. So this is 4. And you have 2n right here. So you'll have 4 is equal to 2n. And on this side, you'll have 1 is equal to n minus m. So this becomes, divide both sides by 2, you'll have n is equal to 2. And on this side, you'll have 1 is equal to, you already know the value of n, so that's 2, minus m. Okay. Subtract both sides by 2, we'll have 1 minus 2 is equal to negative m. Then, we'll multiply both sides by negative 1. So we simplify, this becomes negative 1 is equal to negative m. We multiply both sides by negative m, or by negative 1, so we'll have m is equal to 1. Okay, so this means that our integrating factor is equal to x raised to 1, or that's just x, and y raised to n, which is 2. Because that's the form for our phi, for our integrating factor for case 3. X raised to m, y raised to n. Our m is 1, so we'll have a 1 exponent there for x and a 2 exponent for y, since our n is 2. So now that we have our integrating factor, the next step will be to multiply that integrating factor to our differential equation. So this is our differential equation. So we'll have xy squared times 2x squared over y squared plus 1 dx plus xy squared times x over y dy is equal to 0. So we simplify, this becomes so in this part, the y squared cancels out, so we'll have 2x. So we have x squared here and an x here, so we multiply those two, we'll have x cubed plus xy squared times 1, we'll have xy squared dx plus, in this case, y squared and y, we take off 1 y, and this one cancels out, and we'll have the multiplication of x and x, so the product of x, we'll have x squared y dy is equal to 0. Now this is our new differential equation. So this is the new dE. Or this is basically the one that is multiplied by phi. So now, the next step would be to check for exactness. So when checking for exactness, let's find partial of m with respect to y. Get the derivative of this with respect to y. So we have this one becomes a constant, and this one, we take out the x and get the derivative of y squared, so that is 2y. And on this side, let's get the derivative of this side with respect to x. So we'll have to take out the y, take out the y, or factor out the y. Then we get the derivative of x squared with respect to x, so that is 2x. So if we can see, we simplify this, and we simplify this, the partial of m with respect to y is now equal to the partial of n with respect to x. Therefore, the dE is now exact. Okay, now that the dE is exact, we can now use different methods of solution for finding the general solution. So to find the general solution, since both of them, m and n, are fairly easy to integrate and differentiate, then we can use method 3. Okay, where what we do in method 3 is basically fxy is equal to, we simultaneously integrate m and n. So for m first, we'll have this part, so 2x cubed plus xy squared dx plus g of y is equal to the integral of x squared y dy plus h of x. So when we simplify this, we'll have, so 2x cubed, the derivative of that with respect to x, we'll have 2, factor out the constant, then we get the derivative of x cubed, we'll have x raised to 4 over 4, plus factor out y squared, because y squared is considered constant, then we get the derivative of x, that is x squared over 2, plus g of y is equal to, get the integral of x squared y with respect to dy, or with respect to y, factor out the x squared, then we get the integral of y, that is y squared over 2. Now we simplify even further. we'll have to cancel this out. So we'll have x raised to 4 over 2 plus x squared y squared over 2 plus g of y is equal to x squared y squared over 2. Now cancel out those that are common. And we are left with, or sorry, we have a plus h of x here. Cancel out those that are common in the left and the right side. Then whatever's left is equal to that function. So in this case, g of y is equal to besides h of x, we only have 0. So g of y is equal to 0. And besides g of y, h of x is equal to this part right here. So we'll have h of x is equal to x raised to 4 over 2. Now that we have g of y and h of x, we can surmise the new f of xy. Okay, so the general solution, this now gives us the general solution that we have. So this is f of xy, and we just fill out those that are, or we just fill out all the values. So x raised to 4 over 2 plus g of y such that, or plus x squared y squared over 2 plus g of y, our g of y is 0. So this just becomes is equal to c. So this is our general solution. So that's it. That's it for non-exact differential equations. Follow for more.